Some calculations today. Who likes math? One person? Two?
Yes.
Good news, because this is algebra.
Exactly. I loved Algebra 1 so much.
Me too. Whenever I went to geometry, they wanted to cry every single day.
Yeah, now like I literally I fail every test every day. No, in Algebra 2. Like literally the last grade that I got back in math was 1 out of 9. A 1.
Okay, I'm going to zip through this. Stay with me. Let's go. Stop texting. What are you doing?
That's why
Put
you
your
don't,
phones away.
so you don't send the phone, Sarah.
All right. No gizmos out. Ideal gases do not exist. Write that down. Properties, or here's the definition of an ideal gas. It's a gas that has no forces of attraction, which is impossible. So I'm going to underline that. No forces of attraction. And states that the individual particles that make up an ideal gas have no volume. And that's impossible too. So what that means is if I have a container with gas particles in here, and if this is an ideal gas, which doesn't exist, but if we're making it up and saying, okay, let's say this is an ideal gas, this definition is telling me these dots have no attractive forces for each other, therefore they will just continue to expand away from each other, and that each dot is considered like a point. What does that mean? It's so small compared to the rest of the box that the volume is basically negligible. You know what that means? Negligible? Negligible means you can ignore it. So let's say this box is 5 liters. That little tiny dot, one particle, the amount of space that one little dot takes up compared to the size of the box is insignificant or negligible, right? So have no volume. The volume is negligible. It's a good word to know. Negligible means insignificant. You can kind of ignore it. I'll give you an example. All right, I forget the number, but the mass of the Earth in kilograms, it's an earth science thing and a physics thing. It's in reference tables. I forget the number, but it's really.
I got your science right with me.
Yeah, they might if you can find it quick enough. I don't know. I forget the number, but the mass of the Earth is pretty big. It's a pretty big number. So if yeah, it might have been the physics one, not earth science. Anyways, thanks. That was pretty quick. But I don't think it's it.
I can't find it.
The point is, the mass of Ryan doesn't matter. If we took Ryan off the Earth would still have the same mass. Okay? Think about, anyone have a dog? Okay. How much does your dog weigh, Ashley? Yes. How much? 175? That's a big dog.
Awesome, that is 100 something.
What kind of dog is it? Is it a mix?
Yeah.
It must be a big dog, like a big one.
He's not that
Let's
big.
say 100
He's
pounds.
100.
All right, let's say 100 pounds. The point of the conversation here is sometimes, yeah, sorry. Sometimes dogs get, what organism is living on them?
Did you say
Fleas. So, if you put a dog on a scale, and there's fleas on the dog, and you took one flea off the dog's weight would still be the same. I'm talking one flea. One flea.
You're still taking away weight.
Right, but you can ignore it. The scale isn't going to show it. This, it's,
Well,
How
because
do
the
you strong
fleas
on
don't
scales?
weigh like a pound or anything. Oh my god. I
right.
really don't think
So
I can
guys, stay focused. Don't get on the wrong focus here. The point of this statement and what I said with the flea and the dog is the size of the flea compared to the dog is negligible. You can ignore that weight and the size. It doesn't affect the dog. Same thing with this sample. So that's the only reason I brought that up. We're not going to continue with that. The point of this definition is you need to know it, that this and this makes no sense. It does, just like some of you were just arguing, the flea does have mass. Yes, it does. All right, but again, this statement here is what ideal gases are. Real gases, so those gases that are red, CO2, methane, water vapor, all types of gases, don't follow these rules. So why are we talking about it? Because it helps teach the gas laws.
Go ahead.
Paul first.
Well, I was just gonna ask, in a science which is supposed to be accurate and precise, how can you have something that literally ignores something? So,
It's to help teach theories. So those gas laws can only be kind of taught and understood and calculated in class, in Regents Chem, not in real life measurements, because you ignore things. So you just ignore forces of attraction. So if you take, according to Boyle's law, and you squish a container and the volume decreases, the pressure will go up, and it's supposed to be proportional. It's not always that way in real life because there's actual forces that affect those measurements. So in AP Chem, we talk about that a little bit. And if you did real life calculations, there are these calculations called the van der Waals calculations that take into account these forces, and then you have to do advanced calculations. In school and in theory, we ignore all that, so that's why this is taught, and that's my answer. Yeah.
So like two things. One,
Yeah.
so does like gas have weight or like no? Kind of a stupid question, but does it like?
Well, okay. If you took a balloon that was
Yeah.
empty and put it on a scale,
Yeah.
and then you blew it up with air and sealed it, and put it on the same scale, and it was able to stay on the scale, what do you think would happen?
Oh, I get more heavier.
Would the mass go up?
No,
Then whether it stay the same.
it doesn't get.
So then you're telling me the air has no mass.
Correct.
So the air in this room has no mass
Yes,
at
it
all.
does.
You guys ever pick up an oxygen tank?
Yeah, they're heavy.
Yeah, but the tank itself is also
Tank is
like.
metal.
No, but empty, it's less empty.
You guys ever,
I thought it was just picking up the tank.
did you guys ever, pick up the, like propane tanks you hook up to like a grill?
Yeah, but it's not.
Oh.
Half of that is basically gas. Inside there's liquid, but it's evaporating very quickly, it's volatile. So when it's full, it's pretty heavy. When it's empty, it's pretty light. So, to answer your question,
Yes.
all gases have mass.
Okay.
Now I feel like I need to show you a demonstration.
Please.
Like,
So, not right this second.
Oh,
But yes, Ryan, gases and air definitely have mass.
Oh.
Why? Why is that?
No, but like, honestly, if you put it like the balloon, the tiny
It was
balloon, I understand like the paint tanks are like the big
Hold on, focus. Why or how do we know for certain, without even doing an experiment, gas or air must have
Because
mass?
gravity, you understand how that works.
Forget gravity. Forget gravity.
But like it helps.
I feel like pressure, like isn't
Something like that.
My.
Man, you guys are full of vigor today.
What does that mean?
Oxygen, carbon, some more oxygen, a little bit of carbon and some more oxygen, and nitrogen are in the air. What do these red numbers tell us?
They're mass. They're atomic mass.
So literally every atom in the world has a mass, and that's the mass over there. So if the air is made up of this,
Are we ready?
and nope,
What is
this,
that egg?
and this.
Yeah, those next two.
Yeah, they're
N2, CO2, and O2. If we add up all the masses, this is 28 grams per mole. This is 44 grams per mole. And this is 32 grams per mole. So if I had a box or a container in this room with 1 mole of air, I would have 28 grams of nitrogen in here, 44 grams of CO2, and 32 grams of oxygen. So those numbers, I don't need to do an experiment or show you. I can try and show something with a balloon, but these have already been proven by people way smarter than me that every single atom has a mass. How do I know that? How do you know to take that for what it is? One, you should just believe it because it's there. And two, if you don't like just believing something, what are all atoms made of?
Lithium.
Protons, neutrons, and electrons. How many protons does this have?
3.
3. How many neutrons?
3.
4.
Oh, okay.
How many electrons?
3.
3. A proton. This is a proton. This is a neutron, and this is an electron. Stay with me. This is a long-winded answer to tell you that everything has a mass if it's considered matter.
I can tell it's Monday.
This right here is a mass number. This right here is a mass number, meaning a neutron has a mass of 1 unit, and a proton has a mass of 1 unit. So, if everything is made of protons and neutrons, everything has a mass.
I'm so sorry I asked this question.
Yes.
Okay, dumb question. So,
Today, anything goes.
Which one's on a scale, like this weighs something?
if
Like,
you
this
took
is not weighing.
everyone off of Earth,
Say it again.
if you took every single person
Every
off,
person off Earth.
The mass would change.
yeah, but the mass should
Yes.
No.
More significantly than if one person, but you probably wouldn't even notice it because the Earth gets most of its mass from what?
That's an unimportant.
Water.
What it's made of. Land and water.
Okay.
We are insignificant compared to the amount of dirt and soil and water.
Oh,
I have another question.
Okay, last thing.
You know how like people keep their propane tanks like outside?
I do.
So like during the winter, what happens to the gas inside of it?
Yeah,
Some
why
of
is
it might condense to liquid, but because it's under pressure, that changes things. So pressure, you can alter physical states without temperature changes as long as there's a certain pressure level.
So like,
So it's okay. And plus the freezing point, let's say, is incredibly low. So it would have to be ridiculously cold outside, which humans couldn't live in, for those gases to turn like a solid.
You're gonna have a blast editing this video.
Take your video and just
Yes.
No more questions. Real gases deviate
So,
from ideal gases.
but if you brought water up there, it would, because the pressure is really.
Real gases deviate, write this down, from ideal gases because
still water.
they have forces of attraction and they take up space. They have force of attraction and take up space, also known as volume. The biggest one is right here. And Paul's question was valid. And in AP Chem, we do talk about the van der Waals constants. We don't calculate it in AP Chem, but they do exist because calculations in chemistry are based on the assumption real gases are acting like ideal. Just to make things easier, if you take physics, which all of you should, when you get to physics, a lot of times friction or wind resistance or air resistance is ignored in calculations. In real life, that's crazy. You have to account for that. But when you're learning the theory and just learning in school, the academic part, you ignore some stuff like that just to make it easier to understand the general concepts. So that was a really good point. But here is the point. Real gases do deviate because they actually do have attractive forces between each other. And the biggest thing on the reagents, these two things. Two biggest things they might ask, which two gases on the periodic table are most like ideal? Hydrogen and helium. Which two real gases are most like ideal? And the answer is hydrogen and helium, and that's because their densities are so much lower than everybody else's. They already are very, very, very spread out. So they are already very weak forces of attraction. See, the lower the density, the weaker the attraction. If they're really attracted to each other, they're going to clump together and have a high density. So think of pieces of lead, all right, metal, very dense because they're really, really attracted to each other. So that's why those two are most like ideal. And then the other thing is that question about what conditions make them most ideal, and that's high temp, low pressure. So two conditions that allow real gases to behave most like ideal gases. This is probably the most common gas question that I've ever seen. Out of all the stuff we've been talking about, this one is probably the most common. Two conditions that allow real gases to behave most like ideal. High temp, so you can give it energy to get away from each other, to expand. So high temperature and low pressure. So if you release the pressure and give them a lot of energy, they are able to expand, and that's essentially what ideal gases do. They just expand, expand, expand.
If you make it a really low pressure and a really high temperature, couldn't you accidentally superheat the gases?
Yeah, so if the temperature gets too high, you can start stripping electrons, and then you start turning into plasma like the sun. So yes, that's called the critical point. So when we talk about phase diagrams down the road, bring that back up. All right, so high temp and low pressure, that's the best case scenario for gases to become ideal. All right, can I erase? We're moving on. I still got 4 minutes. I'm using it.
So should we talk about the size of your dog, Dan?
Of my what?
No, of her dog.
Oh,
Absolute beast of a dog.
Yeah, like, I've seen Ollie before, and he's a fair-sized dog. Like, I just...
okay. Write this down here. Gas law calculations. All right. So I'm going to give you a couple practice sample problems here. I wanted to give you some for homework. We'll see what happens here.
It's okay, you don't have to.
Yeah. Right. So
Forgive you.
a sample of neon gas with a volume of 1.5 liters and a pressure. These get kind of long-winded, so stay with me. A sample of neon gas with a volume of 1.5 liters and a pressure of 101.3 kPa is allowed to expand to a volume of 3.0 liters. Calculate the new pressure, parentheses here, assuming temperature is held constant. So, what I'm introducing here, and I highly doubt you're going to have homework.
Oh wait, isn't this the one thing you told us to practice?
It wasn't that on our homework.
Yeah. When I wasn't here, you had that book problem. Yes, very similar to this. Yep. So just write that equation down too in your notes here. It's called the combined gas law. It's on the back of the reference tables. We're going to use that the next couple of days. Well, here until the bell, or until I let you go. Bells haven't really been working too well, but the P1 V1 over T1 equals P2 V2 over T2 is used for questions like this. The nice thing on the Regents is most of the time you don't have to use all the variables in that equation. So as you're writing this down, if you're understanding a little bit, the liters is volume, the kPa is pressure. I'm telling you the temp is held constant. So what that means is you don't need the T's. The temperature is not needed in that equation, so you can just erase them. It just becomes P1 V1 equals P2 V2. So some of you might be confused. I'm going a little quick here at the end, but I'm going to show you how to set this up, hopefully, and then we'll just pick up with this tomorrow. But this is a typical question where you're using that equation. So you have to first learn the relationships with the graphs, understand the concepts, and then apply it to calculations. And you know what? I guess I'll probably just stop here. The bell's going to ring, or it's going to be 28 very soon here. So we'll pick up with this tomorrow. And that's it. You will have homework due Wednesday. Yeah, sorry, Bridget. So I got one sheet. The other one, I don't know what happened to it.